Hello everyone. This is the presentation of the final work of Quantum Communication and Computation Seminar. Our group is formed by Linde, Gyssels, Macià, Amorós, Hesham, Fadl, and me, David Linde. Well, for the first exercise, we compute the information between x and y, and we can model the channel xy as a binary symmetric channel with the probability of error 1/2 multiplied by 1 minus sinus of theta. So the mutual information can be expressed as a function of the error. And this is the formula that we have followed. The information between x and y is 1 minus the entropy of the probability of error.
Okay, so I will explain the computation of the mutual information between x and b. As we can see, this first formula defined in the class slides shows us how we can compute this quantity. But before using this formula, we need to define rho sub b. And to define rho sub b, first we need to define rho sub xb. Rho sub xb can be defined using this sum of cron products, which we implemented with MATLAB using this code. Here, first we define a symbolic variable called theta, and with this theta an angle that we pass to the theta 0 and theta 1 vectors, which are vertical. And also we define the x0 and x1 verticals, vectors, which also are vertical. On the last line, we actually implement the formula from the previous slide to compute rho sub xb using the cron function in MATLAB and just a product of a vertical vector with a horizontal vector. And this operation leads to a 4x4 matrix. From this matrix, we can compute the partial trace to get rho sub b, and it's done just applying this definition. Now that we have rho sub b, we can compute the von Neumann entropy, and to do so, we created a small function to which we pass a matrix, and we compute the eigenvalues of this matrix. With these eigenvalues and eigenvectors, we apply the formula that we see at the top of the slide, which computes the sum of all these matrices times the eigenvalues, and finally we compute the negated trace. Now that we know how to compute the entropy and we can get this rho sub b, we can implement this mutual information function. So we can compute the mutual information as a function of theta, and the plot will be showed. The plot will be showed in the future, and Hesham will explain it.
Hello, so I am Linde Gyssels. I will be talking about the next exercise. So the assignment is to prove that the set lambda y is a proper positive operator valued measurement. And first, let's say, as the assignment says, x is uniformly distributed over the set 0, 1, 2, 3. So this means that the chance for every possible value is 1/4. The density matrix, the composite density matrix in x and b to the third is defined as, I've written down the sum over the Kronecker product about the two density states with the chance p. The chance p, the probability p, we can take out of the summation because it's 1/4 for every value of x. And so this is the general formula for that. And the assignment said that lambda y is defined as in the second formula. So to calculate lambda y, we need to know row b to the third, which is defined as the partial trace of row xb to the third. And to calculate the trace, there's also a general formula for that I've written down on the third line, the third equation. Proving that lambda y is a POVM, therefore we have to prove two different properties. That the eigenvalues for every lambda y is positive or zero, so lambda y has to be positive semi-definite, and the summation over y of lambda y, for all the lambda y, has to be the identity matrix. So we can start with the second one. So we sum over all the different lambda y's, and since rho is not a function of y, we can take that to the left side of so we can take that out on the left side and on the right side. So the second term in the equation has shown that, and since Vy is a complete set, this means that the summation over this ket psi y and the bra psi y is the identity matrix. So then we can take, so this is just 1, and we can simplify this equation to 1/4 rho b to the third to the minus 1 equals 1. Rho b to the third to the minus 1 is the pseudo-inverse of rho b to the third, because rho b to the third does not have a real inverse. Unfortunately, no one of us was able to prove this, or even to calculate rho b to the third. It's given here in this formula, but nobody was able to calculate rho b to the third, or to then calculate the pseudo-inverse. So this is a property that we were not able to prove. Also, since we were not able to calculate rho b to the third, well, we cannot calculate lambda y. Also, we don't know psi y. So these formulas are really general, and nobody really knew how to calculate it or how to apply some properties of the slides to it. So we were also not able to prove its or to calculate its eigenvalues.
We also want to remark that for this von Neumann entropy computed on the first exercise, it goes smooth. But when we tried to do the last exercise, in which the rho sub b is a 8x8 matrix, this eigenvalue function from MATLAB doesn't give a proper result, because it just runs indefinitely, and we didn't know how to proceed at this point. So we weren't able to do the last exercise.
Hello everyone, I am Hesham Fadl, and I will introduce the output plot of the accessible information between x and y, and the quantum mutual information between x and b, as the theta ranges from 0 to pi. We can see here in the plot that the mutual information is always larger than the accessible information. The mutual information is shown in blue, and that indicates basically that a large reduction of uncertainty happened. And when the theta is equal to pi over 2, the vectors are orthogonal, and therefore the probability is equal to 1, as the maximum value as shown here in the graph. Finally, as a conclusion, the transmission of a classical random variable through a classical quantum channel has some challenges, as the information detection occurs by subjecting the channel to a measurement in order to determine the state, and if the states are mutually orthogonal, then the optimal orthogonal measurement can be performed, which would determine the state correctly with a probability equal to 1. But if the given states are not orthogonal, then no measurement will allow to distinguish perfectly between them. Therefore, we construct a measurement optimized to distinguish between the non-orthogonal pure quantum states also. We can formalize this as a quantum detection problem, and therefore we seek a measurement that minimizes the probability of a detection error. Thank you so much.